In September 1859, astronomers witnessed an extraordinary and unprecedented event, a powerful solar flare erupting from the Sun. This eruption unleashed an immense amount of radiation, energy, and plasma material into space, marking what we now call the first recorded solar superstorm. Considering the flare took place over 93 million miles away, one might assume it posed little threat to Earth. Yet, within hours, its effects reached across continents, bringing unanticipated consequences. Telegraph lines throughout Europe and North America suddenly malfunctioned, sparking unexpectedly and even igniting fires. It was then that people began to understand that the Sun, a constant source of light and warmth, could also be a source of unseen danger. Scientists later dubbed this remarkable event the Carrington event, after the British astronomer Richard Carrington, who observed the flare. Thankfully, the incident occurred in the mid-19th century, when technology was relatively simple and less dependent on electricity. However, as we move further into the digital age, scientists have warned that in 2025 we could face even more powerful solar storms, triggered by events called coronal mass ejections, or CMEs. A CME is a massive cloud of plasma, charged particles from the Sun, that hurtles through space at immense speeds. During a CME, the Sun can eject billions of tons of material in a single burst, and if this solar cloud is directed at Earth, it can arrive within as little as 15 hours, with the bulk of its impact lasting several days. As the charged particles travel through space, they capture and accelerate other particles in their path, which further intensifies the CME's energy and power. When this wave of solar material finally reaches Earth's magnetic field, it disrupts our planet's upper atmosphere, heating it and causing it to expand. This increased atmospheric density affects satellites, causing them to slow down and lose altitude. Communications dependent on satellites, such as GPS and Internet services, become unreliable, resulting in data transmission issues and positioning errors. Furthermore, the surge of charged solar particles can overwhelm power grids, overloading transformers and potentially causing blackouts. A solar storm strong enough to damage power stations could plunge entire cities into darkness, halting communications, internet access, and social services. These interruptions could lead to severe economic and social consequences, including the potential for widespread economic instability. The problems don't end there. Power plants are also responsible for running water systems, heating, and other essential services. In the event of a prolonged outage, water distribution and heating could come to a standstill, grocery stores would be unable to process sales without cash, and basic necessities would become harder to access. A major solar event could even threaten global food supplies. For instance, modern agriculture relies on GPS-linked tractors and equipment. When geomagnetic storms interfere with these systems, farming operations can grind to a halt. The disruption in food production would only compound the challenges faced by society. Maritime navigation, too, relies heavily on satellite technology. With damaged or degraded satellites, ships at sea would lose their navigation abilities, potentially putting their crews, cargo, and critical supplies at risk. Animals, as well as humans, can be affected by magnetic disturbances. Many species, such as whales and migratory birds, use Earth's magnetic field to navigate. When this field is disrupted by a solar storm, animals can lose their sense of direction, which has ecological implications that scientists are only beginning to understand. In the midst of all these effects, human health may also be impacted. Although scientific consensus is still emerging, it's thought that magnetic disturbances could influence human blood pressure and mood, particularly in those with pre-existing cardiovascular conditions. Many people report experiencing headaches, high blood pressure, or a general feeling of unease during geomagnetic storms, though it remains unclear if these effects are a direct result of solar activity or a placebo effect stemming from increased awareness of the storms. A notable example of the potential severity of these solar events occurred on March 13, 1989. 3 days earlier, on March 10, the Sun released an enormous CME, containing an amount of material equivalent to the mass of 36 Earths. The CME raced toward Earth at over 1 million miles per hour, reaching our planet's magnetic field in just a couple of days. The result was a geomagnetic superstorm that created a spectacular aurora display across much of the northern hemisphere, painting the sky with vibrant colors. However, this beautiful display came at a cost. The storm was so intense that it penetrated Earth's atmosphere and reached the planet's surface. Satellite operations were disrupted, and electrical grids suffered significant damage. In New Jersey, a transformer at a nuclear power plant failed, and in Canada, systems became so overloaded that power outages swept across northeastern regions, leaving 6 million people without electricity for 9 hours. This was the largest power outage on record caused by a geomagnetic storm. As solar activity continues to increase, some scientists predict that we may face even more intense solar storms by 2025. While it's impossible to prevent these storms, researchers are working to better understand the sun's cycles and predict future events. If scientists can forecast an impending storm, we might be able to temporarily power down certain systems, reducing the potential for widespread outages. In the future, advanced shielding technology or protective materials could be developed to safeguard critical infrastructure, helping us to better prepare for these powerful space weather events. But what causes these solar storms, and why are they so disruptive? To understand this, picture the sun's magnetic field as a tangled mess, like hair that becomes knotted after a restless night of sleep. As the sun rotates, these magnetic fields twist, stretch, and eventually snap, releasing vast amounts of energy in a process known as magnetic reconnection. This is the mechanism behind solar storms, with the most significant types being CMEs and solar flares. A solar flare is a sudden, explosive burst of radiation that includes electromagnetic waves, X-rays, and ultraviolet light. Traveling at the speed of light, these flares reach Earth in just 8 minutes. Although Earth's magnetic field and atmosphere shield us from the worst effects, strong flares can still disrupt radio signals, affecting both military and civilian communications. In addition to solar flares, there are radiation storms, swarms of high-speed electrons and protons that approach nearly the speed of light. While Earth's magnetic field protects the surface from these storms, they can be hazardous for astronauts, high-altitude flights, and satellites. Exposure to these charged particles can lead to radiation-like effects, posing serious health risks to anyone in space. Yet, amid these risks, solar storms have a captivating side. The interaction between charged solar particles and Earth's atmosphere creates the stunning auroras we see near the poles. These light shows, known as the Northern and Southern Lights, offer a reminder of the beauty of space and the complex relationship between Earth and the Sun. The possibility of future solar storms is a growing challenge for modern society. But with continued research and new technologies, we can work toward mitigating their effects. The Sun, our life-giving star, serves as a constant reminder that space is as beautiful as it is unpredictable. With vigilance and preparation, we can face the unknown while marveling at the wonders of the cosmos.